Picture this. It's 480 BCE, and the fate of Western civilization is about to be decided by a wooden boat with 170 men crammed inside it, pulling oars in perfect rhythm. The Persian Empire, the largest military force the world has ever seen, is bearing down on Greece with over 1,000 ships. But the Greeks have something special up their sleeves, a weapon so revolutionary, so perfectly engineered for naval warfare, that it's about to change the course of history forever. Welcome to the world of the Trireme. You might think ancient shipbuilding was just a bunch of guys with axes randomly chopping up trees and hoping for the best. Wrong. Dead wrong. The construction of a Greek trireme was more precise than a Swiss watch and deadlier than a viper's bite. These weren't just boats. They were floating missiles designed for one purpose, ramming enemy ships into splinters while moving faster than anything else on the Mediterranean. Before we dive into the incredible engineering behind these ancient speed demons, make sure to hit that subscribe button, smash the like, and drop a comment about what fascinates you most about ancient naval warfare. Your engagement helps us bring more amazing historical content your way, and trust me, you're going to want to stick around for what's coming next. The story begins in a bustling Greek shipyard, probably somewhere along the coast of Attica. The air is thick with sawdust. The sound of hammers on wood echoes across the harbour, and skilled craftsmen are about to turn a pile of timber into the most advanced warship of the ancient world. But here's what makes this absolutely mind-blowing. They're doing it without blueprints, without power tools, and with mathematical precision that would make modern engineers weep with envy. The first challenge any shipbuilder faced was selecting the right wood. This wasn't a trip to Home Depot. This was life or death decision-making. Pine was the go-to choice for most of the hull because it was light, flexible, and wouldn't waterlog as quickly as other woods. But here's where it gets interesting. Different parts of the ship required different types of timber. The keel needed to be oak, tough as nails and straight as an arrow. The ram at the front, the business end that would be smashing into enemy hulls, was often made from the hardest wood they could find, sometimes even reinforced with bronze. Finding trees that were long enough and straight enough for a trireme keel was like finding a unicorn in your backyard. We're talking about timber that needed to be over 120 feet long without a single major flaw. Some shipyards would send scouts into the mountains for months, searching for that perfect tree. When they found one, the entire community would celebrate because they'd just found the backbone of their next warship. The process started with something called scarfing the keel. Imagine trying to join two massive pieces of wood, end to end, so perfectly that the joint is actually stronger than the original timber. The craftsman would cut intricate interlocking joints, kind of like the world's most important jigsaw puzzle. Except if you got it wrong, your entire ship might split in half during the first storm. Here's where ancient Greek engineering gets absolutely wild. They used a construction method called shell-first building, which is the complete opposite of how most people think boats are made. Instead of building a skeleton frame first and then adding the skin, they started with the outer hull planks and worked inward. It's like building a house by starting with the siding and then figuring out where to put the studs. The planks had to fit together tighter than a miser's purse strings. We're talking about joints so precise that they could hold back the Mediterranean Sea without caulking. The secret was in the cutting. Each plank was shaped with hand tools until it matched its neighbour with tolerances that would make a modern machinist jealous. Some of these joints were so tight that when the wood swelled from seawater, the hull became practically watertight. But getting the planks to fit was just the beginning. The real magic happened when they started adding the internal framework. Remember, this ship needed to be light enough to reach incredible speeds, strong enough to ram through enemy hulls, and flexible enough to handle the stress of 170 men pulling oars with the fury of the gods. The frames that went inside the hull weren't just randomly placed support beams. Each one was carefully calculated to distribute stress throughout the entire structure. The Greeks had figured out principles of load distribution that wouldn't be formally understood by engineers for another 2,000 years. They were doing advanced structural engineering with nothing but experience, tradition, and an incredible understanding of how forces work on a moving ship. Now comes the part that separated the Trireme from every other ship of its time, the rowing system. This is where Greek naval architecture went from impressive to absolutely revolutionary. They had to figure out how to fit 170 rowers into a hull that was only about 120 feet long and maybe 18 feet wide. Do the math. That's less than 1.5 feet per rower. It should have been impossible. The solution was pure genius. They stacked the rowers in 3 levels. The top level, called the Threnites, sat on outrigger seats that extended beyond the hull. The middle level, the Zygites, sat at the main deck level. The bottom level, the Thalamites, sat below deck with their oars poking through ports in the hull. Each level had its own specific oar length and rowing angle, all calculated to maximize power while preventing the oars from clashing with each other. Building the rowing benches, or thwarts, required the precision of a clockmaker. Each bench had to be positioned at exactly the right height and angle. Too high, and the rower couldn't get proper leverage. Too low, and the oar would hit the water at the wrong angle. The spacing between benches was critical too. Give the rowers too much room and you're wasting precious space. Too little, and they can't get a full stroke. The outrigger system for the top level of rowers was an engineering marvel in itself. These weren't just planks stuck to the side of the ship. They were carefully braced structures that had to support the weight and pulling force of nearly 60 men while adding as little weight as possible to the overall vessel. The Greeks solved this by using a combination of lightweight timber and strategic bracing that distributed the load back into the main hull. Here's something that will blow your mind. The oar ports had to be positioned with mathematical precision. Each port was cut at a specific angle to allow the oar to enter the water cleanly and exit without catching. Get the angle wrong by even a few degrees, and your rowers would be fighting the ship instead of powering it forward. The bottom level ports were the trickiest because they were so close to the waterline, too low, and water would pour in. Too high, and the oars wouldn't bite the water properly. The mast and sail system added another layer of complexity. When the Trireme was under sail, it could cruise at a reasonable pace without exhausting the crew. But when it came time for battle, that mast became a liability. The Greeks designed a system where the entire mast could be quickly lowered and stowed, along with all the rigging. In battle configuration, the Trireme was pure rowing machine. No sail to catch the wind, no rigging to get tangled, nothing but sleek hull and 170 pairs of oars. The bronze ram at the bow was where all this engineering culminated into a weapon. This wasn't just a pointed piece of metal stuck on the front. The ram was carefully shaped to punch through enemy hulls while distributing the impact force back through the entire structure of the attacking ship. The angle, the weight, the mounting system, everything was calculated to turn the entire Trireme into a 40-ton missile that could punch through the side of an enemy vessel and back out again before the enemy knew what hit them. Building one of these rams required master metalworkers who understood both bronze casting and the physics of impact. The ram had to be heavy enough to do damage, but not so heavy that it affected the ship's balance or speed. Some rams weighed over 400 pounds and were works of art as much as weapons of war, often decorated with the eyes of sea monsters or the heads of gods. The joining of the ram to the hull was perhaps the most critical connection on the entire ship. This joint had to absorb the tremendous shock of ramming while keeping the weapon securely attached. The Greeks used a combination of bronze bolts, wooden reinforcements, and careful shaping to create a connection that could survive the violence of naval combat. What made all this construction even more impressive was the timeline. A skilled shipyard could complete a Trireme in about 3 months, working from sunrise to sunset. That's building one of the most sophisticated machines of the ancient world in less time than it takes most people to renovate a kitchen today. The quality control was intense. Every joint was inspected, every plank tested, every measurement checked and double-checked. The men who built these ships knew that 200 lives would depend on their craftsmanship. One weak joint, one miscalculated angle, one shortcut in the construction, and an entire crew could end up feeding the fishes. The real test of all this precision engineering came when the ship hit the water for the first time. Launch day wasn't just a celebration. It was the moment of truth when months of calculations either proved themselves or sent everyone back to the drawing board. The Greeks had this down to a science, but it was still nerve-wracking every single time. Picture the scene. Hundreds of workers, their families, city officials, and probably half the neighborhood gathered around as this sleek war machine prepared to taste salt water for the first time. The ship would be positioned on wooden rollers, carefully angled toward the water. Teams of oxen or dozens of men would slowly ease the trireme down the beach until, splash, it either floated like a cork or sat in the water like a very expensive rock. But floating was just the beginning. Now came the really tricky part, trimming the ship. This wasn't like adjusting the mirrors in your car. This was about finding the perfect balance point for a 40-ton vessel that needed to perform like a racehorse. The ship had to sit just right in the water, with the ram at exactly the correct depth, and the oar ports positioned perfectly relative to the waterline. The master shipwright would wade around the hull with a measuring stick, checking the water level at dozens of points. Too much weight in the bow, and the ram would drag through the water, slowing the ship down. Too much weight in the stern, and the bow would ride too high, making the ram less effective. Finding that sweet spot required moving ballast stones around, like pieces on a chessboard, until everything was perfect. Here's where it gets really interesting. The trimming process had to account for the weight of the crew. A trireme with just the shipyard workers aboard sat completely differently than one loaded with 170 rowers, 30 marines, and all their gear. The builders had to calculate exactly how the ship would behave when fully crewed and loaded for battle. Get it wrong, and your perfect warship would handle like a drunken whale when it mattered most. Once the basic trim was sorted out, it was time for the moment every shipbuilder both dreaded and anticipated, the first rowing trials. This is when all those carefully calculated oar ports, bench positions, and spacing measurements would either prove their worth or reveal themselves as expensive mistakes. The initial crew wasn't made up of experienced rowers. They were usually shipyard workers, local fishermen, and anyone else willing to grab an oar and see what happened. The first attempts were usually disasters. Oars clashing together like a percussion section gone mad, rowers bumping into each other, and the ship wandering around the harbour like a lost tourist. But gradually, as the crew figured out the rhythm and timing, something magical would happen. The chaos would transform into coordination, and suddenly, this collection of wood, bronze, and human muscle would start moving through the water with purpose. The stroke rate was everything. Too fast, and the rowers would exhaust themselves in minutes. Too slow, and the ship wouldn't build up the momentum needed for effective ramming. The Greeks discovered that the optimal combat stroke rate was around 40 strokes per minute, fast enough to generate serious speed, sustainable enough to maintain for the duration of a battle. But reaching that rate required training that would make modern athletes weep. Professional trireme crews didn't just row, they became part of the machine. Each man had to know not just his own stroke, but how his timing affected the rowers around him. The top-level rowers had the longest oars and the most leverage, so they set the pace. The middle level had to match their timing exactly, while the bottom-level rowers worked in the most cramped conditions, pulling their oars through ports just inches above the waterline. The training regimen was brutal by any standard. Crews would start with short sprints, maybe 500 yards at maximum stroke rate, just enough to get the blood pumping and test the ship's top speed. A well-trained trireme crew could push their ship to nearly 10 knots during these sprints, which was absolutely blazing fast for the ancient world. That's faster than many modern sailing yachts can manage, but sprint speed was useless if you couldn't sustain it when it counted. Combat rowing required a different kind of endurance, the ability to maintain a steady, powerful stroke for hours at a time while maneuvering for ramming attacks. This cruising stroke was slower, around 25-30 strokes per minute, but it could be maintained for most of a day if necessary. The most challenging training exercises involved tight turning drills. A trireme's greatest advantage was its ability to outmaneuver larger, heavier ships, but pulling off a sharp turn at speed required incredible coordination. The rowers on one side would suddenly reverse their stroke direction, while the other side maintained forward power. Done correctly, the ship would pivot like a dancer. Done poorly, and oars would snap, rowers would be thrown from their benches, and the enemy would have plenty of time to prepare for whatever sloppy attack was coming their way. The training also had to prepare crews for the psychological shock of combat. Ramming another ship wasn't just about technical skill, it required nerve. You had to maintain perfect stroke timing while enemy arrows flew overhead, while the enemy ship loomed larger and larger in front of you, and while every instinct screamed at you to duck or flinch or do anything except keep pulling that oar in perfect rhythm. Mock combat exercises became elaborate productions. 2 triremes would face off, practicing ramming runs without actually making contact. The attacking ship would build up speed, aim for the enemy's side or stern, then veer off at the last second. The defending ship would try to turn and present its own ram, or backwater frantically to avoid the attack. These exercises taught crews how to read the water, judge distances, and execute split-second maneuvers that could mean the difference between victory and a watery grave. But even the best-trained crew was only as good as their equipment, and that equipment took a beating during normal operations. Oars snapped, rope rigging stretched and frayed, and the constant stress of rowing opened up seams in the hull planking. A trireme crew had to be part sailors, part warriors, and part maintenance technicians. Broken oars were the most common problem. With 170 oars in constant use, something was always breaking. Smart crews carried spares, lots of them. A typical trireme might have 20 or 30 extra oars stowed along the center line of the ship. But even with spares, swapping out a broken oar during combat required split-second timing and nerves of steel. The procedure went like this. The moment an oar snapped, the rower would shout a warning to his benchmates. The spare oar would be passed forward from storage, usually hand to hand down the length of the ship. The broken oar would be pulled inboard and the spare slotted into place, all while maintaining the stroke rhythm. A good crew could make this swap in under 30 seconds without breaking their cadence. A poor crew would lose momentum, fall out of rhythm, and probably lose the battle. Hull maintenance was even trickier. The constant flexing of the ship during high-speed maneuvering would work the planks loose, opening gaps that let in seawater. Small leaks could be plugged temporarily with anything handy, cloth, rope, even bread if nothing else was available. But serious leaks required more drastic measures. The most common emergency repair was relashing the hull planking. The Greeks used a technique where they'd pass ropes completely around the ship's hull, then tighten them like a giant belt. This would squeeze the planks back together and buy time to reach port for proper repairs. The procedure required men to go over the side of the ship with ropes, often while underway and sometimes while under fire. Rigging maintenance was a constant battle against salt, sun, and stress. The lines that controlled the steering oars had to be checked daily, and the leather wrappings on the oar handles needed regular replacement. A steering line that parted at the wrong moment could send the ship careening into a reef or straight into an enemy ram. The most critical maintenance task was keeping the bronze ram sharp and properly seated. The repeated impacts of ramming attacks would gradually loosen the bolts holding the ram to the hull. Before each battle, crews would inspect every bolt, every brace, and every connection point. A ram that came loose during an attack would not only fail to damage the enemy, it might punch a hole in your own ship's bow. What made all this maintenance even more challenging was that it had to be done at sea, often in rough conditions, and sometimes while being chased by enemy fleets. There were no dry docks in the middle of the Aegean, no machine shops, no hardware stores. Everything had to be fixed with whatever materials and tools were aboard the ship. The crew organization that made all this possible was as precisely engineered as the ship itself. The 170 rowers weren't just a mob of strong backs. They were organized into a hierarchy that would make a modern corporation jealous. Each level of rowers had its own officers, its own responsibilities, and its own pay scale. At the top of this floating pyramid of power sat the Trireme, not just the captain, but the guy whose personal fortune was probably tied up in every plank of the ship. See, here's something that'll blow your mind. Wealthy Athenians were expected to personally fund these warships as a form of public service. Imagine being told by the government that your civic duty involves dropping the equivalent of several $1 million on a single boat. Talk about expensive patriotism. The Trireme wasn't necessarily the best sailor or the most experienced warrior. He was the guy with the deepest pockets and the biggest stake in making sure this floating investment didn't end up as driftwood. But smart Triremes surrounded themselves with professionals who actually knew what they were doing. The Kybernetes, or helmsman, was the real brain behind the operation. This guy could read wind patterns like a weather app, judge distances better than a surveyor, and make split-second decisions that would either win battles or get everyone killed. Below the helmsman sat the Keleusts, the stroke caller who set the rhythm for all 170 rowers. This wasn't just about keeping time, it was about reading the battle, knowing when to call for maximum speed, when to order backing water, and when to signal the intricate maneuvers that could thread a trireme through enemy formations like a needle through cloth. The Keleustis had to have the lung capacity of an opera singer and the timing of a master drummer. One missed beat, one poorly timed command, and the whole ship would fall apart like a house of cards in a hurricane. The rowers themselves were divided into 3 distinct classes based on where they sat. The Thranites, those top-level rowers with the longest oars and the best view, were the elite. They got paid more, they got more respect, and they had the most influence when it came to ship politics. These guys were like the senior partners in a law firm. They'd earned their positions through years of experience and proven skill. The middle-level Zygites were the solid middle class of the rowing world. Experienced enough to handle the complex timing, strong enough to pull their weight, but not quite prestigious enough to earn a top-deck seat. The bottom-level Thalamites had the toughest job of all, crammed into the hull with barely enough headroom to sit upright, pulling their oars through ports just inches above the waterline. These guys rowed by feel and sound, since they could barely see what was happening outside. Here's what made this system really work: cross-training. A good rower didn't just master one position, he learned all 3 levels. This meant that if someone got injured or fell overboard, any experienced crew member could slide into the empty seat and keep the ship moving. It was like having a sports team where every player could play every position. The Marines aboard a trireme were a different breed entirely. While the rowers focused on making the ship move, the Marines were there to fight once the ramming was done. These weren't just soldiers who happened to be on a boat. They were specialists in naval combat, trained to fight on wet, tilting decks while dodging flying oars and falling rigging. A typical trireme carried about 30 Marines, which might not sound like much until you realize these were elite troops armed with the best weapons of their day. Bronze-tipped spears, reinforced shields, and enough attitude to clear an enemy deck faster than you could say surrender or swim. Their job wasn't just fighting, they also served as shipboard security, making sure the rowers stayed focused on rowing instead of mutiny. The real genius of trireme crew organization was how it balanced individual skill with collective action. Every man had his specific role, but everyone understood how their job fit into the larger machine. The Marines knew not to interfere with the rowers during maneuvers. The rowers knew to duck when the Marines needed to launch their spears. The officers knew exactly how long they could push the crew before exhaustion set in. But all this perfect organization meant nothing if the crew couldn't perform when it counted. And in 480 BCE, with Xerxes' massive Persian fleet bearing down on Greece, it was about to count more than it ever had before. The numbers were staggering. Over 1,000 Persian ships against fewer than 400 Greek vessels. On paper, it looked like a massacre waiting to happen. The Persian ships were bigger, carried more soldiers, and had the backing of the largest empire the world had ever seen. But they had one crucial weakness. They weren't triremes. Most of the Persian fleet consisted of converted merchant vessels, ships built for carrying cargo, not for the lightning-fast attacks that trireme warfare demanded. They were like bringing a freight train to a Formula One race. The Greeks understood that their only chance lay in superior tactics and ship handling. They couldn't match the Persians in raw numbers, but they could outmaneuver them, outrun them, and outfight them in the confined waters where trireme advantages really showed. The key was choosing the right battlefield. Somewhere the Persians couldn't use their numerical superiority effectively. The stroke rates that crews had drilled for months suddenly became matters of life and death. A trireme pulling 40 strokes per minute could accelerate from a standing start to ramming speed in less than a minute. That acceleration gave Greek commanders the ability to strike fast, back off, and reposition for another attack before the heavier Persian ships could respond. During actual combat, the coordination required was absolutely mind-boggling. Picture this. You're one of 170 rowers packed into a ship that's racing toward an enemy vessel at nearly 10 knots. Arrows are flying overhead, enemy ships are maneuvering to ram you, and your own ship is executing turns so sharp that the deck tilts at crazy angles. Through it all, you have to maintain perfect stroke timing while trusting that the guy calling the shots knows what he's doing. The ramming attack itself was poetry in motion when executed correctly. The attacking trireme would approach at maximum speed, aiming for the enemy's side just behind the ram. At the last possible moment, the crew would ship their oars, pulling them inboard to avoid having them snapped off by the impact. The bronze ram would punch through the enemy hull with a sound like thunder. The impact would throw both crews around like rag dolls, and then came the tricky part. Backing off before you got stuck. A successful ram attack could hole an enemy ship in seconds, but if your ram got stuck in their hull, you'd both go down together. Smart trireme crews practiced the backing maneuver as much as the attack itself. The moment after impact, the rowers would reverse their stroke, the steering oars would be thrown hard over, and everyone would pray that the ram would pull free cleanly. The psychological effect of a successful ramming attack was almost as important as the physical damage. Nothing broke enemy morale quite like watching a sister ship disappear beneath the waves in a matter of minutes. One moment she was there fighting alongside you, the next moment there was just debris and swimmers in the water. It was the kind of thing that made even veteran crews think twice about continuing the fight. But ramming wasn't the only tactic in a trireme's arsenal. Sometimes the goal wasn't to sink the enemy's ship, but to disable it. A skilled crew could sweep alongside an enemy vessel and use their oars like a giant comb, snapping off the enemy's oars and leaving them helpless in the water. This technique, called diekplus, required incredible precision and timing. Come in too close and you'd damage your own oars. Too far away and you'd miss entirely. The most spectacular maneuver was something called the periplus, essentially a high-speed flanking attack where one trireme would race around behind an enemy ship and ram it in the stern. This attack was devastatingly effective because it hit the enemy's weakest point while avoiding their ram entirely. But it required split-second timing and nerves of steel, because if you miscalculated the turn, you'd end up presenting your own vulnerable side to the enemy's ram. What made these tactics possible was the incredible power-to-weight ratio of a properly built trireme. with 170 rowers generating roughly 37 horsepower, more than many modern outboard motors. These ships could accelerate, turn and maneuver in ways that seemed impossible for their size. A trireme could go from a dead stop to 8 knots in under 60 seconds, execute a 180-degree turn in about 4 ship lengths, and maintain combat speed for hours if necessary. The endurance factor was crucial because naval battles in the ancient world weren't quick affairs. A major engagement could last from sunrise to sunset, with ships constantly maneuvering, attacking, retreating, and repositioning. Crews had to pace themselves like marathon runners while maintaining the explosive power needed for ramming attacks. It was like asking a sprinter to run a marathon while occasionally throwing in some 100-yard dashes at full speed. Food and water management during these extended battles became a matter of survival. A trireme crew would burn through their energy reserves faster than a sports car burns gas. Smart commanders made sure their ships carried extra rations and water, but storage space was always at a premium. Every square foot dedicated to supplies was space that couldn't be used for weapons, spare equipment, or additional crew members. The medical challenges were equally daunting. When 170 men are pulling oars in perfect synchronization and something goes wrong, people get hurt fast. A snapped oar could break ribs, a sudden maneuver could throw rowers from their benches, and combat inevitably meant arrow wounds, spear thrusts, and the occasional man overboard. Trireme crews had to be part sailors, part warriors, and part field medics. The ship's physician, when there was one, had his work cut out for him. Treating injuries on a moving, rolling platform while potentially under enemy fire required skills that modern emergency room doctors would respect. Battlefield surgery with bronze tools, herbal remedies, and a lot of hope was about as advanced as medical care got in 480 BCE. But perhaps the most remarkable thing about trireme warfare was how it turned individual human effort into collective military power. Each rower contributed maybe a quarter horsepower to the ship's total output. But when multiplied by 170 and coordinated perfectly, that individual effort became something that could change the course of history. It was democracy in action, not in the political sense, but in the physical reality that every man's contribution mattered equally to the ship's success. The social dynamics aboard a trireme were fascinating too. You had wealthy citizens sitting alongside freed slaves, professional sailors working with farmers turned rowers, and everyone depending on everyone else for survival. Social class mattered a lot less when your life depended on the guy next to you pulling his oar in perfect time with yours. This egalitarian aspect of trireme warfare probably contributed to the development of Athenian democracy. When your military success depends on the coordinated effort of ordinary citizens, those citizens tend to expect a say in how things are run. The trireme wasn't just a warship, it was a floating lesson in the power of collective action and shared responsibility. As the Persian fleet approached Greek waters in 480 BCE, all this training, all this engineering, and all this social innovation was about to face its ultimate test. The fate of Greek civilization would be decided by how well these wooden ships and their human crews could perform under the ultimate pressure. Everything they'd learned about building, sailing, and fighting these remarkable vessels would be put to the test in battles that would echo through history for the next 2,500 years. The crews preparing for battle knew that raw speed meant nothing without tactical intelligence. And that's where the trireme's design philosophy really showed its genius. These ships weren't just built to be fast, they were built to be smart. The low profile that made them so sleek also made them nearly invisible on the horizon until they were close enough to strike. Persian lookouts scanning for threats would see the towering sails of their own fleet, but might miss the lean silhouettes of approaching triremes until it was far too late to react. The Greeks had turned stealth into an art form, but not the kind you'd expect. They couldn't make their ships invisible, but they could make them unpredictable. A trireme formation could appear to be heading in one direction, then suddenly pivot and strike from a completely different angle. The key was in the communication systems that Greek crews had developed over decades of practice. Hand signals, flag positions, and even the angle of oars could convey complex tactical information across an entire fleet without alerting the enemy. A slight change in rowing rhythm might signal an imminent attack to friendly ships, while sounding like normal propulsion to enemy ears. The lead ship's Kelliustas wasn't just calling strokes for his own crew, he was conducting an orchestra of destruction that could involve dozens of vessels. But here's what made Greek naval tactics absolutely revolutionary. They understood that the real battle wasn't between ships, it was between information systems. The side that could process battlefield intelligence faster and communicate decisions more effectively would win, regardless of numbers. Persian commanders, used to fighting on land where you could see the entire battlefield at once, suddenly found themselves trying to coordinate 1,000 ships spread across miles of ocean with no way to communicate except through messengers rowing frantically between vessels. Greek trireme squadrons, meanwhile, operated like wolf packs. Each ship knew its role, its position relative to the others, and exactly how to respond to changing conditions without waiting for orders from above. When a Persian formation showed a weakness, nearby Greek ships could exploit it immediately, while the Persian admirals were still trying to figure out what was happening. The psychological warfare was just as important as the physical combat. The sound of 170 oars hitting the water in perfect unison was unlike anything most sailors had ever heard. It wasn't just the splash of oars, it was the sound of absolute coordination, of human and machine working in perfect harmony. Enemy crews, who heard that rhythmic thunder approaching, knew they were facing something special, something that their converted merchant ships couldn't match. The Greeks played up this intimidation factor deliberately. Crews would sometimes coordinate their approach so that multiple triremes would emerge from behind islands simultaneously, their bronze rams gleaming in the sunlight, their oars moving like the legs of some massive sea creature. The visual impact was devastating. One moment the horizon was empty, the next it was filled with the most advanced warships in the world, bearing down at impossible speed. Training had prepared Greek crews for the sensory overload of battle, but nothing could fully simulate the chaos of actual combat. The smell of sweat, salt, and bronze mixed with the smoke from fire arrows, the sound of splintering wood when rams found their mark, the screams of men going overboard in full armour, the crash of oars snapping under impact. Through it all, the stroke callers had to maintain their rhythm, and their crews had to respond like the precision instruments they'd trained to become. The most experienced crews developed an almost supernatural awareness of their ship's condition during battle. A subtle change in the feel of the oars might indicate hull damage. A slight shift in the ship's balance could mean they were taking on water. The sound of the stroke, the way the oars bit into the water, could tell veteran rowers whether their ship was performing at peak efficiency or starting to struggle. Emergency procedures that had been drilled countless times in peacetime suddenly became matters of life and death. When a trireme took a ram hit that didn't sink her immediately, the crew had maybe minutes to assess the damage and decide whether to fight on or attempt to beach the ship. These decisions couldn't wait for committee meetings or careful deliberation. They had to be made by men who understood their ship better than their own homes. The repair techniques that crews used during battle were nothing short of miraculous. Imagine trying to plug a hole in your ship's hull while enemy vessels circle like sharks, arrows fly overhead, and your own ship is still maneuvering for attack positions. Some crews developed techniques for emergency patching that could be executed without even bringing the ship to a stop. Canvas patches pre-soaked with pitch, wooden plugs carved to standard sizes, and emergency rigging repairs that could be completed in the time it took to execute a single ramming run. But the most crucial repairs were often the simplest ones. A broken oar handle wrapped with rope and leather, a steering line spliced back together under fire, a cracked thwart reinforced with whatever wood was handy. These weren't elegant solutions. They were battlefield medicine applied to wooden ships. Quick fixes designed to keep the vessel fighting long enough to win or escape. The endurance demands on trireme crews during major battles were absolutely staggering. Modern athletes train for years to maintain peak performance for a few hours, but these ancient rowers had to sustain combat-level output for entire days while making split-second tactical decisions. The physical conditioning required was unlike anything we see in modern sports. Part marathon runner, part powerlifter, part gymnast, all wrapped up in someone who could function effectively as part of a 70-man team. Nutrition during battle became a critical factor that most people never think about. A trireme crew burning calories at combat rates would exhaust their energy reserves faster than a modern race car burns fuel. Smart commanders learned to rotate their ships in and out of direct combat, giving crews brief opportunities to rest and refuel. Some fleets developed floating supply ships that could provide fresh water and food to fighting vessels without requiring them to leave the battle entirely. The Greek innovation that really set them apart was their understanding of combined arms tactics. While each trireme was formidable individually, they were devastating when coordinated as a fleet. Different ships would take on specialized roles during battle. Some focused on ramming attacks, others on boarding actions, still others on disrupting enemy formations or cutting off escape routes. The most elite trireme crews could execute maneuvers that seemed to defy physics. Ships passing within oars' length of each other at full speed, coordinated turns that would bring multiple vessels to bear on a single target simultaneously, and breakthrough attacks that could punch holes in enemy lines faster than the defenders could react. These weren't just displays of seamanship, they were military tactics refined to the level of art. As the Persian fleet finally came within sight of the Greek positions, every crew member knew that decades of innovation, training and preparation were about to be tested against the largest naval force ever assembled. The engineering that had gone into every bronze fitting, every calculated angle, every precisely placed oar port was about to prove whether Greek naval technology could overcome Persian numbers. The fate of Western civilization was riding on the performance of these remarkable machines, and the men who had learned to become one with them. When the smoke cleared and the last Persian ship disappeared over the horizon, the trireme had proven itself as more than just a warship. It was a revolution in human engineering that changed the course of history. Think about it. A wooden vessel powered by nothing but human muscle had just defeated the most powerful empire on Earth. The Battle of Salamis wasn't won by magic or divine intervention. It was won by precision engineering, relentless training, and the kind of coordinated teamwork that wouldn't look out of place in a modern Formula One pit crew. The numbers tell the whole story. A typical trireme measured 120 feet long, carried 170 rowers, 30 marines, and a handful of officers. The oars ranged from 13 to 14 feet long, with each rower pulling roughly 200 pounds of force per stroke. At combat speed, these ships could hit 40 strokes per minute, generating enough power to ram through enemy hulls or outrun anything else on the Mediterranean. Under sail, they could cruise at 4 to 5 knots all day long. Under oars, they could sprint at nearly 10 knots, speeds that would make modern yacht owners jealous. But here's what made the trireme truly special. It proved that superior technology and training could overcome raw numbers. The Persians had more ships, more men, and more resources, but they didn't have the engineering precision or crew coordination that Greek shipbuilders and sailors had perfected over generations. Every carefully calculated angle, every precisely positioned oar port, every hour of synchronized rowing practice had led to this moment when David didn't just beat Goliath, he sent him running for the hills. The legacy of the trireme extends far beyond ancient naval warfare. These ships pioneered principles of lightweight construction, efficient propulsion, and coordinated teamwork that still influence ship design today. More importantly, they demonstrated that free citizens working together could accomplish things that seemed impossible when facing overwhelming odds. The trireme wasn't just the sharpest tool in the Aegean. It was proof that human ingenuity, properly applied, could change the world. So, the next time you see a sleek racing yacht or a high-performance rowing shell, remember that you're looking at descendants of those ancient Greek warships. The trireme may have been built from wood and bronze, but its real construction materials were human intelligence, determination, and an absolute refusal to accept that bigger always means better. Sometimes, the most revolutionary weapon isn't the biggest or the most expensive. It's the one that's built exactly right and crewed by people who know how to use it. Use.